Hey everybody, I'm Nguyen-Tu, and this is Lab 3 of Physics 2212. The purpose of this lab is to use the principles of energy conservation and current conservation to predict the behavior of circuits containing resistors in series and parallel, and examine the behavior of ohmic resistors and capacitors. In this lab, I'll be applying the law of conservation of energy, which states energy cannot be created or destroyed in the form of Kirchhoff's loop rule that states the sum of all the electric potential differences around a loop is zero. I will also be applying the law of conservation of charge, which states the total amount of electric charge in a closed system must remain constant in the form of Kirchhoff's node rule that states all the current that flows through one junction must be equal to all the current that flows out of the junction, and applies to both conventional and electric currents. In addition, I'll be using Ohm's law and the formula for capacitor potential difference, along with the formulas for resistors and capacitors in series and in parallel. To complete this lab, I will be following the 7 steps listed here. The main result of this lab is that given measurement rounding error, the CCK model measurements match their calculated prediction values in Part 1 series circuit, while in Part 2 RC circuit, the calculated RC value was approximately 6.024 seconds, with the light bulb starting bright and then dimming to off as the capacitor becomes full from empty or empty from full. In both parts of this lab, the 3 main assumptions are 1. The resistance of both wires and ammeters are negligible, 2. The internal resistance of the voltmeter is infinite, and 3. The online circuit construction kit from the Colorado PHYS2212 project makes accurate models of real-life circuits. For setup, in both parts the system was the circuit and the surroundings was nothing. For initial conditions, time was paused while the circuit was being set up, so no current was flowing during setup, and the capacitor in all 3 variations of Part 2 began empty, although the capacitor in the 30 ohm setup had measurements recorded only after the capacitor was full. In the first step of Part 1, I found that the ammeter measurements matched the predicted current measurements, after rounding to the hundredths place. After inserting one of the ammeters backwards, the reading stayed the same, which indicates that the ammeter in the CCK reports the magnitude of the current, since it was expected that the number would be negative. After replacing the ammeter with the voltmeter, it read a negative 3.00 volt reading as expected because of the combined 3 volts from the 2 batteries, while the ammeter reading became 0 since the circuit is now an open circuit, so no current is actually flowing. Since the voltmeter has internal infinite resistance, it does not complete the circuit and does not allow current to flow. After measuring the potential differences of each component in the circuit, I found that, as expected by the loop rule, the round-trip potential difference sums to 0. Shown here is an approximate graph of potential relative to the negative end of the battery versus position around the circuit. In all of the earlier cases, attaching the voltmeter to the circuit never changed the ammeter readings, despite altering the circuit, because it essentially has infinite internal resistance and thus allows no current to flow through it. Now, replacing the voltmeter on the left with an ammeter in parallel with a 100 ohm resistor, the current through the other ammeter increases by 0.04 amps, because adding the parallel ammeter that has no resistance allows the path of least resistance, skipping the 100 ohm resistor, for the current to flow through. From the measurements gathered in Part 1, these are the resistance values calculated for each component. In Step 1 of Part 2, with the 10 ohm light bulb, the capacitor took approximately 8.4 seconds to fully charge and another 8.4 seconds to fully discharge. In both cases, the current started strong and then decreased to 0, with the light bulb respectively starting bright and then dimming to off. Replacing the 10 ohm light bulb with the 20 ohm light bulb, the behavior of both light bulb and current stayed the same, while it took longer to fully charge and discharge at approximately 11.6 seconds and 14.1 seconds respectively. After replacing the 20 ohm light bulb with a 30 ohm light bulb and fully charging the capacitor, the 20 seconds worth of voltage versus time data as the capacitor discharges is shown in the form of a table and natural log delta V over delta V naught versus time plot here. From the data, the actual RC value was calculated to be 6.024 seconds and matches the expected RC value of 6 when rounded to the ones place. In this lab, there are 3 main possible sources of error. First, the CCK project rounded values to the hundredths place, which likely caused the differences between the measured values and the expected values. 2. The wires and ammeters might have resistances greater than the expected 0, which would cause the calculated values to be incorrect. 3. The voltmeter might have internal resistance significantly not infinite. Like 2, this would cause errors in the experiment calculations. Unlike assumed in this experiment, real ammeters have a slight resistance that would drop some of the voltage and result in less current being measured for the circuit it is hooked up to than if the ammeter was not connected. Therefore, conducting this experiment in real life would likely result in lower readings of the currents than what was reported in this experiment that used ideal ammeters. In the ideal model, where wires are assumed to have no resistance, the capacitor reaches full charge significantly quicker than in real life, since wires, capacitors, and batteries in real life have resistances that will slow down how quickly the real-life capacitor can be charged.